Okay, hello everybody, this is Dr. Schultz, and this is the first video that is going to be part of a three-part video on vector math. So this first video is going to walk you through the first page of your packet. Let's read the learning targets. The learning targets for this lesson are going to be that you will learn how to represent vectors graphically, that you will learn how to multiply vectors by scalars. You will learn how to resolve vectors into their components. You will learn how to add and subtract vectors graphically. You will learn how to add and subtract vectors algebraically, and how to multiply vectors by other vectors. I want to stress that you can use additional resources here for help, especially the physics classroom. So please have a look at that. It's the lesson on vectors and motion and forces in two dimensions. So let's start off with the definition of a vector quantity. What is a vector quantity? And we would say that a vector quantity is any quantity with both size and direction. We learned about vectors last year in physics, and we know that vectors are very important in describing motion. And so you can think about vectors such as a position vector, which we represent with the letter x, and sometimes we'll put a little arrow over it. We also know that displacement is a vector. Other examples would be velocity, acceleration, force, and there are quite a few examples of quantities that have both a size and a direction. Okay, so vectors are very visual tools in physics, and so when we talk about representing vectors graphically, we would say that we can represent them using arrows. Okay, so if I want to represent a vector, I can say, let's say that I want to represent a displacement vector. I could say that the displacement is plus 2 meters. And I could also represent that vector with an arrow that points to the right, and I could scale it with plus 2 meters. This end of the vector is called the tail, and this end of the vector is called the head. Okay? And so the arrow represents that vector nicely. If I wanted to change that, I could say, well, what if another displacement vector goes the other way? I could represent that by drawing an arrow that points in the other direction, and then I could make the length half as much. Okay, so that would be another displacement vector. 1 second. So those are a couple of ways that you can represent the vectors graphically. How about indicating direction with vectors? Okay, you can do this different ways. Let's say that I have a vector that goes this way. Maybe it's a position vector. One way to represent the direction of that would be to say that it's pointing kind of northwest, right? And you could say let's put directions here, north, east, south, and west. And you could talk about that angle. You could say that that angle might be 30 degrees west of north. And that would work. So you could say 30 degrees west because you have to go west if you start at north. Another way to indicate that same angle, or that same vector, would be to say that you have to go 60 degrees north of west. And of course that's just the complement to 30 degrees because they add up to 90, but notice that we have to switch the labels. So be okay with that. Understand that west of north and north of west refer to the two different angles, and know which is which. Another way of indicating angle is a little bit more standardized. Let's take the same vector, let's put it here, and now let's talk about this angle that is measured from the positive x direction. And of course, if we wanted the full angle, we would take 90 degrees and add the 30, so this would be 120 degrees from the positive x direction. And that's actually the way that we will probably use the most in this class, is to always refer to that positive x direction as our reference direction. Okay, last thing on this page is the statement that vectors can always be moved around and remain unchanged. So if I have this vector that's shown here, and I simply move it over, I keep the same length, and I keep the same angle, these vectors are the same. In fact, I could move that vector up, and as long as I don't change the length or the direction, that's okay. Okay, so I could even move it out here. And so you can imagine just pushing that vector around. All of these vectors are exactly the same. Okay, it doesn't matter where they start. So as an example, think about displacement. The displacement doesn't depend on the specific starting point, just on the change. Now, if you change the direction or the size, then it makes a difference. So if I took this vector now and I drew it like this, and I kept the angle the same, but I made the length much bigger, that's not the same vector anymore. Okay? Or if I took this vector and I now tilt it up this way, so it has the same length, but it has a different direction, these are not the same. Okay? So these vectors are all different. In this case, it's a different direction. In this case, it's a different size. So if you stretch a vector, or if you squeeze it, meaning if you change its length, you change the vector. Or if you twist the vector, you also change it. Okay, so to summarize here, we've talked a little bit in this first video about how to represent vectors graphically by drawing them. And we've talked about the fact that they have both a size and a direction, and that arrows are the way that you can use, are a tool for representing those vectors.